In the last, I think, lecture, we are talking about a little more theoretical part on the linear regression, and actually we went through a specific set of example, at least one example for which we have shown that okay, how you can actually make your own model, a mathematical way of solving a linear regression problem, and as well as we actually used the SciPy linear regression package directly to solve the problem, and we are getting a similar results, right? Exact same result, and that was the discussion yesterday we did. So I just want to continue on that direction because that there's some specific thing which I need to discuss on that. So for today, what I decided not to go for any like sort of presentation, directly go to the Google Colab notebook and try to show or to discuss what exactly I am planning today. So I'll go through this Google notebook a little bit slowly because if I realized like after yesterday's class, I realized that maybe I need to little bit slow regarding when I'm showing some results or some code in Google Colab, because some of you already not that much of like aware of writing a code in Python. So what I'll do, I'll slowly go through this Google Colab node today and try to build up what exactly the topic we're going to cover today. Okay, so it is just a continuation of that regression thing, and as I said that yesterday we already solved some linear regression, right? So we'll start with some same kind of problem first. So these are the packages which I already talked about yesterday. So you can you know that like for if you don't want to write your own linear regression model or straight line fitting code, then basically you can directly import linear regression function from sklearn directly, and that you can use for your problem. So yesterday I was talking about all the mathematics discussions, everything beginning regression. So in this notebook, I'm not going to again do the same thing, but what I'll do, I'll directly, whenever I need to solve any regression problem using this linear model, then actually I'm directly calling this linear regression function. Okay. So now I just start what exactly I have done here. So let's say is it fine to everyone? Like I are able to see my screen? Is it fine, right?
Yes. Yes.
Okay, so right now I'm just making some simulated data because right now I don't have any real data. So what I'm doing here, I'm just generating some data set. So I'm just considering n equal to 20. This is the number of data points I'm considering right now, and I need to fix some slope intercept, right? As we know that like for linear regression, we're going basically you're writing in the y equals to in terms of some linear relation on independent variable x, that is mx plus c, right? So your m basically slope and c is the intercept. So you can define your slope is, let's say for this case 1.5 and intercept 2.5, but these are the free parameters, so you can choose whatever you want, right? Now after that, what I did, I just generate a set of uniform points in between 0 to 2, right? So this function, this x equals to, so I what is written here that basically those who not aware of Python, so what I did here, I just call this first this function that is basically part of numpy random class, and this function is random state. Okay, so I define this function first as a new variable, that is rnd, right? And then actually I'm calling rnd dot uniform. So rnd already have some set of distribution, so you can call normal distribution, uniform, so whatever you want. So right now I'm just calling uniform distribution. Okay, so when you're calling uniform data distribution in between some range, let's say a to b, and how many points you want to generate, this function will generate those set of points. Okay, so right now it only generates some point in between 0 to 2, and the number of points should be equal to 20, right? And after that, actually I sorted out those numbers, because when you're generating uniformly in between 0 to 2, right, it is not generating in a sorted order. So better to sort them. So that's why I just use a sort function directly. It is a part of the data structure when you're writing your x in terms of some array. So now you can directly sort them using this sort function, and after using this one, it is already sorted out, right? Okay, so x is already generated, using a uniform distribution into in between 0 to 2, right? So now once I know what is x, I can generate y also, right? Because y is nothing but mx plus c, right? So I can say this is y equals to mx plus c, right? So I know what is my m, what is my c, and I already generate some x also, so I can generate y also, right? So this is just a simple data generation just for our exercise. So we are actually generating some similar data, and that is simple data we are generating. Now if I just plot the data, right, so then basically you can see this is basically the data. So this is x-axis, so it should be plt dot x level. Okay, so this is my data, right? So it's basically it's already in a straight line, right? Now what are the basic thing we need to check, that okay, this x, what's the shape of the x, right? Since it has only 220 points and it should be an array structure, so it has basically 20 number of points. And you can also check what is the mean and max, right? Because you have given a range in between 0 to 2, so if it is working correctly, then it should be the mean and max range should follow the given range, right? So it is right now it is in between 0 to 0.4 and 1.93, right? And that means it is actually in the range, in that range which actually we are right now looking for. So this is 0 to 2. One important thing that none of you have to ask me that this question, if you have any queries or anything that I missed, just ask me. There is no point of waiting for me. So now the point is why I need this thing, right? Only thing you can say, okay, I can directly write an np.random state dot uniform here also, or this random class already have another direct function. You can directly call uniform function or normal function, whatever distribution you want, directly from numpy.random. So then why this is important? This is important because right now you can see I just fix a seed, right? So that means if I fix a seed here, always if I generate a set of uniform numbers for x, the number will be same, right? Right now, since I maybe before today's lecture, I run this code, right? I get some other results if I not fix the seed, right? And during the class, maybe I'm getting some other results, right? So then it's very difficult for me to describe what exactly I was thinking and what exactly I'm getting here, right? So for now, when you are working with some specific some random state, it is better to fix the random state such that whenever you're running the same code, you will actually generate the same data points. Otherwise, like every time your data point will change, and based on that your analysis may be changed, right? And that can be very difficult for others to understand. So so that's why this is the normal habit, that when you're calling some random function, it is better to fix a seed first. So here till I fix the seed 42, that means whenever I'm running the same Google Colab, let's say several times, every time I'm getting the same data points, these points. So if I not fix, then obviously this data point can be varied. That means that this mean and max can be varied in between that range. Does it make sense?
Yes, sir. Yes.
Okay, one important thing that I just print what is the shape of this x, right? Ideally, this x is basically a vector with 20 data points, right? So it has 20 data points, but it is not in a actually array representation. In array representation, actually you need to be shape should be 20 is because it's a dimension of one row, so it should be one column, so it should be 20 comma 1, but that was not the case. So what you need to do, you need to reshape it in terms of just 20 comma 1. So right, so if I just print here, just a minute. So if I print here, you can see this is actually part of one array, right? All the value of x. Now what I did, I just reshaped that x with minus and 1, and that actually give you me a new, like I'm just saving that same data into a new variable that is called xa, x arranged, that is shape of 20,1, and that was important because when you are calling going to, I'll show why it is important. But if you just print this xa, right, you will see the values are exactly same, right? So the values are exactly the same, are stored in the new variable xa, but you can see this structure of data. Now it has individually there is a bracket, right? That means basically these are part of one array where actually individual data points actually are the first, second, third, like this kind of elements of that array. Whereas when actually you're writing in this representation, it is just a one array and it has all the elements. So this kind of representation is required when actually you're calling some specific function from your packages, Python packages. Right now I need to call this linear regression function. So if I plug in here, let's say if I plug in x, right, then it will give some error. And since I know that, that's why I did that. But if you not make this kind of representation, and if you work with this representation, then what will happen that you'll get some error. And what error is the error is already written here, right? So you can see that it's written, the error is basically expected 2D array got 1D array, right? So that means this representation is a 1D array because it is just an array which has all the numbers, whereas this, it has two bracket, right? Two third brackets of this is the first third bracket right here, and this is the second one, right? So this is just two-dimensional representation of the same data. So that means the second dimension is not there, but data structure is a two-dimensional, right? So when you're calling this linear regression function from this sklearn, it expect the way it is written, it's expect 2D array. Okay, and that's what it's written that okay, reshape your data. So it's also giving a like suggestion how we can resolve the issue. So you're saying that reshape your data either using array, reshape this function. Okay, and so that's why I reshape my array or the x variable in terms of this way, right? So this reshape is actually a suggestion which probably someone can get once they're writing, they are sending some x in a one-dimensional representation, right? So based on that suggestion, I did that, and therefore if I plug in xa here, it should run. Right now it's working, right? Does it make sense? I hope so, right? Okay, so this linear regression, basically the linear fitting, which yesterday we covered almost within 1 hour, right? But now you can say this is just one liner. If you're directly going to call one function from the psyche, sklearn, right? Now it is already fitted. So now what I can do, you can calculate what is the r square, right? That is the error actually I already discussed yesterday. So what I told you yesterday that okay, if r square is towards 1, that means your fitting is good. If it is towards 0, that means fitting is not good. And if it is negative, that means it is completely it is not at all related to that data, right? So here actually it is 1. That what that implies that basically your actually the fitting is perfect, right? And now you can see from this model, you'll get intercept value equal to 2.5 and slope equal to 1.5, right? And that was the true value of your intercept and slope to generate the data, right? Because if you remember, I use slope of 1.5 and intercept 2.5, right? So this exactly match with the when it was generated data. So let's say that was the ground truth. So this value is exactly matching the ground truth, right? Now it's what is implies basically, then basically implies that if I plot the prediction, then basically you'll get that the straight line actually exactly matching those data points, right? Does it make sense? Fine, perfect, right?
Sir, but
Yeah,
it was expected, right?
Sorry, I'm not able to hear you properly.
It was expected, right, sir? We have some set of random numbers. We have just used the y equal to mx plus c formula with x as that random variable.
Exactly.
So
exactly. It is expected because we generate the data set in a straight line, right?
Yes, sir.
Yeah. So if you generate it in straight line, you should fit the straight line properly.
Right.
So it is not a big deal. But if you remember yesterday when I was showing the example, their data point are not in a straight line, right?
Right, sir.
So in that case, obviously, whatever the base fitted straight line you're getting, that should be your final fitting, right? So different people can come up with different fitting of that data, and whatever the R square value is like higher for that, that was the best option, best fitting, right? But for this case, since all of the data points are in the straight line, so if everyone doing separately based on their own algorithm, everyone should come up with this solution.
Yes.
Okay, so that means in real scenario, in real practical scenario or real life, you are not expecting data in a straight line, right? Right. And that's why we can say that, okay, ideally, when you're treating a straight line, we are assuming the data actually are in a linear relationship, but that was not the true case. So we are expecting some noise, right? So that's why I just wrote that, okay, now from now onwards, when actually I'm generating this data, y, I not only I need to write y is a function of m, x, and c. Also, I need to add some noise also, right? So if you remember here, actually when actually I'm generating this, is writing this y, right? Here I'm writing in terms of only y plus mx plus c. But next time onwards, when I'm going to generate this y, I should also add some noise, right? So this is the real scenario. So now onwards, what we'll do, we'll consider some noise. Now the question is, how you know what kind of noise it has, right? So we don't have any idea what kind of noise we have. So what we can do, we can actually estimate, or we can pre-assume something about noise, right? So the first option, so maybe I can start with this one.
So like we can take the noise to be a normal random variable, right? Or
Yes. So we assume that, okay, whatever the noise is there, that means the data are not in straight line because of some addition noise, and that can be coming from some distribution, right? So now that is depending on what kind of system you are solving. So that noise can be uniform, coming from uniform distribution. That noise can come also from a Gaussian distribution. That's up to you, right? So right now I will be showing two different cases. So first option, what I can consider that, okay, I'm assuming that that noise part is actually coming from a normal distribution, right? So I'm assuming here that this noise basically is coming from some normal distribution, and that fluctuation obviously I've given as a small fluctuation. So it is a small perturbation. Otherwise, if I give a very high perturbation, then obviously it's like a very noisy data, right? So then it doesn't make any sense. So what I did, I just add some perturbation in terms of some noise, and that is in between in between 0.1 to 0.2, right? So this is the normal, this is the noise part I generated. So I generated 20 data points, noisy data points, right? And then actually I'm adding into the actual y, right? That means this part we already have, this part we already generated, right? And now I'm generating this noise from a Gaussian distribution in between 0.1 to 0.2, and then I'm adding with this part, right? And that is my final y, or new y. Does it make sense?
yes, sir.
Perfect. So this is the first option. Okay, so now I generate a new y, and obviously for that, what you expect that those data points should not be in a straight line, right? So if you plot the data points, you can see these are the basically fluctuation at those points, considering this y error. So I plotted that x, y, and y error, and these are the different for individual point. These are the variance or the deviation from the data point you are expecting, right? So now if I just plot the previous y and new y, right? So previous y is shown by this red dots, right? And this new y is shown by the navy blue dot, right? Now it's clearly shown that, okay, previously obviously all of them are in a straight line, so it's still like it looks like a straight line, whereas after perturbation or after adding noise, these points actually changed, right, little bit, and therefore it is not in a straight line. Fine. So right now we are going to work with this new data points, right? And we will see how this linear regression model can actually, what kind of fitting it can give, right? Now we can write the same, you can again call the same linear regression function for this new data. So obviously that xa is fixed, we have not changed x data, right? So we only change the y. So this now I'm just passing this y, and now you can see that okay, I'm just getting another fitting, right? Now you can see the fitting is 0.96, right? That means the fitting is not that bad, right? And you can expect what is the intercept, what is the slope we are getting. That is 2.51 and 1.53, right? So that means basically the error in the slope is basically 0.014 and 0.03, and the error in the intercept is basically 0.014, right? Fine. Any question?
No, sir. No, sir.
Okay, good. So now basically if you plot them, then you can see this is the fitted straight line for that, and these are the data points right now. Okay. So far so perfectly fine. Now I can also change the second option. So what is the second option for us? So I just given two examples. One is that okay, I'm considering noise from a Gaussian distribution, which we already tried. And second, actually, I'm considering that okay, noise actually coming from some uniform distribution in between same range. And actually, once it is coming from uniform distribution, what you are doing that okay, whatever the new y we are generating, that is actually coming from some Gaussian distribution. So that's why this noise and the previous or the actual y are passing through this normal distribution, and we are generating some y new that can be a Gaussian distribution. So this is another option, and then for that you will see this kind of deviation, and these are the new data points, and then if you fit the model, then also you're getting a good fitting, and then also you're getting this kind of thing, right? So fitting can be possible with a noisy data also, but that noise has to be a it should be a small perturbation rather than like making a higher, very high perturbation, right? Now up to that is very clear. I hope so. Now what we'll try to estimate or try to visualize this noise part, like how we're going to analyze this noise, right, in terms of statistics, because in real scenario we don't know what is the m and what is the c, right? So always you need to estimate what should be the estimated final solution in terms of m and c, and how you can design or how you can actually make a solution in terms of some statistical analysis, right? And so what I'll do, I'll just show you that what kind of visualization you can get from this kind of example. Now what actually I did here, so this is just a simple function. How many already aware of function?
So we are.
All of you?
We are aware of it.
Yeah. So those who are not aware of, so for that, like normally, like a function has a very like specific structure. What you need to pass, some parameter for which you're going to like return something. So we are passing some parameter here. This is one variable that is called params, and that is another variable that is called x, right? And what I'm writing here, that okay, I'm just basically from this function I'm returning basically y, that is mx plus c, right? So s and I, s for slope, I for intercept, and basically you are multiplying slope into the x and plus intercept, right? And that is basically a linear model, and that exactly same as your y, which we defined earlier. So that actually we define just for when we're going to call, we'll call this function now. In terms of the error, what is the error we can measure? Yesterday I talked about the r square, but right now we'll try to like see the visualization in terms of very basic error, that is basically the absolute error, right? Absolute error is nothing but like for each data point, you know what is the actual value and what is the estimated value or the predicted value from your model, and you can divide it by that sigma, which actually basically the noise part, right? So we know what kind of noise we have added, so we can easily like plug in the actual y, the predicted y, and the noise which we added into the model, right? So this you can calculate, and absolute is basically you can take the mod of that, and that is basically, and take the sum, it's basically absolute deviation, and the square deviation basically if you take the square of that. So these are the two different noise error representation, and for that we will see what kind of visualization you can get from this kind of error part. So these two function basically is written to to get back this individual absolute deviation and square deviation. Okay, so if there's no question, I'll go through the like these two functions quickly. Yeah.
So like why we use absolute deviation when we have like mean squared error thing, right?
Yeah, mean square error is your score, right? This is basically one statistics for which you are by which you can decide your result is good or bad, right? But I'm just showing here that if you want to see if you want to visualize in terms of in a like let's say I have a 2D space in a slope and intercept, right? How this error can vary or change over that space.
Okay, sir.
Okay, so you can do the same exercise with maybe R square or or some other error, but for R square, it is basically the difference is like that right now. For this case, what I can do, I can directly choose some value of, let's say, M and C, and I can get back whatever the error I'm getting, right? But in for R square, basically you need to feed the model and you need to get one value for one solution, right? So there actually you can't vary different M and C and get the same results right now. So that means if you want to make the same visualization for this R square, then basically you need to fit different set of equations, right? But right now I'm not just like solving different equation. I'm solving same equation by varying only M and C, and I want to see that in M and C space how actually this error is propagates.
Okay, sir.
Okay, so this is just a simple standard error, right? You know that normally whenever first of all in statistics, this I don't want to go to that part, but like in terms of theoretical part, normally when you're defining the Gaussian distribution, right, that's basically like e to the power minus y x minus x mu x mean divided by sigma square, right, and then the whole square, right? So basically what you're not actually you're calculating, basically you're calculating the absolute difference between your x divided by the mean, right? Whereas here actually you're basically calculating the difference between your actual data points and the predicted one. So this kind of representation is going to help you if for the visualization of the error in terms of that M and C space. Same for the similar for the second one, it's basically the square of the whole thing, right? And that is basically equivalent to some chi-square distribution. So normally to make similar kind of analogy, we normally try to see how error can propagates through the space of M and C by this kind of error. So you can define your own error term also if it is statistically sounds valid. Okay.
Yes.
Okay, so as I said that what I'll do, I'll just try to see if I vary an M and C, then actually how actually the error is propagated through this space, right? So then what I do, I need to define a 2D grid, right? So right now I'm in a space. In x-axis the slope and y-axis basically intercept, right? And in that space, what I can do, I can make a set of points, right? And that can be think this can be like a mesh grid point over a 2D space. Okay, so right now we are considering basically a 256 plus 256 grid. So what I did, I just generate a set of mesh grid point here. So this just generating a set of basically it's just a box. This is a square box, and it's actually generating between the given slope. So I know what is slope, actual slope, right? So it is in the range of plus minus 2 of the given slope, and as well as the plus minus of 2 of the intercept, right? So basically I know what is the actual slope intercept, and I'm just extending that box by plus minus 2, and I'm making like this mesh grid. So how if you're not aware of the mesh grid, so I just give an example here. So let's say I just choose x actually linspace in between 0 to 4. So basically you can print x, so it's basically, or I can just say so the x is in between 0 to 4, right? So all the values are in between 0 to 4. Similarly, if you print y, so then you're getting in between 0 to 1, and these are the data points. So I don't know how to length. So anyway, so now for this for this boundary, or for this box, So we already fixed the box, right? The width and the height of the box, yeah, by considering x and y, the range of x and y, right? And now what I need to generate some some value in those points, considering my function as a this function. So this is y into sine piece. This is sort of a nonlinear function, and for which actually we want to calculate what should be the value at different grid point of that space, right? So what I need to do, I need to first fix the range or the length or width of the box, and then I need to define that function for which I need to compute these values, and then I need to make a mesh grid. So this x and y actually make a mesh grid on that given range of x and y, and then I can calculate what should be the value of z in basically the value of this function, at those mesh grid point, and then I can plot it, right? So it is just simple representation that, okay, this is x-axis, this is y-axis, and this z-axis basically is another dimension, 3D, because it is a 3D space, and at all this z point or all this 3D points, actually you are calculating what should be the value, considering different combination of your x and y, right? So this is just a representation of a mesh grid. Does it make sense?
Yes.
Okay, so same thing we are doing also here. So we are fixing the box, the width and the height of the box, considering the actual slope plus minus 2 of the actual slope, and similarly plus minus 2 of the intercept thing. So that will give me the range of that overall box, and for that we are generating a mesh grid, and then actually what we are doing, we are actually calling that function for which we need to calculate the value, right? So we need to calculate the value for this function, this error, right, for different point in that space or in the mesh grid. Similarly for that, right? So I just define these two different functions, that function vals 1 and then function vals 2, where actually I'm storing all the values of this absolute deviation or square deviation, considering the combination of different mesh grid point, right? So this is actually I'm just calling that function. Okay, does it make sense?
Sir, what is this np.v step?
Oh, so that actually is simple. Like I can show you, but I have not shown here. But maybe to understand that, I need to do is like separately. So just give me just a minute. I will show you what exactly visually it represents. So let's say first we did a lens space, right? So this S grid and I grid, these are two variables where actually we only define the range, right? So what we expect from that? Someone can tell me what should expect if I just print this part?
So like array with range slope minus 2 to slope plus 2.
Yes, fine. Similarly for I, right? So I no need to do that then, right? So it is just those points, right, for which you need to make a mesh grid. Right. Now, when I'm talking about mesh grid, basically it's a combination of both point, right?
Yes, sir.
So now you can say, okay, let's say I made a mesh grid. Sorry, I made a mesh grid, right? So now if I print this, what should I expect?
A grid of 26 points.
Yeah, so I ideally should give a combination of 2D point, right? It should be a coordinates. So individual element should be coordinates of two, combination of both, right? So let's say as maybe I can show it again here. Sorry, it's little bit. Let's say I'm just printing this and this.
The first part.
Yeah, so I'm just printing the first point, right? So ideally, like when you're defining the mesh grid, it should give you a coordinate in terms of minus 0.5 and 0.5, right? That is because that is the one point for which you need to calculate the error, yes, right? Because this is your value of m and c at that space, right? But actually, in the NumPy mesh grid function, it actually provides you individual coordinates. Like this x contains all the x coordinate, and I contains all the y coordinates, right? So then actually you can't send both are separately, right, to your function, because your function requires as a coordinate.
Yes.
Right? So then what I need to do, I need to basically, now you can say that from this structure, they have a two-dimensional representation, right? Because as I use the X as a two-dimensional data earlier. So now actually it's also two-dimensional data, right? But ideally it is not, the second coordinate is not, second dimension is not there in this case. So what I can do, I can use this Ravel function, which actually flatten the array. Okay. So when I'm using this sgrid dot Ravel, it is flattened the array, right?
Yes.
Okay. Now this array is flattened, and similarly the second array also flattened, right? And if I stack them together, then it will be a coordinate system, right? It is a 2D data points.
Right.
Right. So that's why I'm just stacking them vertically to make them 2D coordinates. Right. So it's like that. Okay. When you are calling this mesgrid function, it's actually providing two different array. One array contains all your x1, x2, x3 like that, and another array actually contains all y1, y2, y3, yn. Right. Now, if it is actually it's in a one-dimensional representation, then you no need to use any Ravel thing, because it is already in a flattened part, right? But since in our case it is not a like a flat one, so we need to first make it flat, convert into 1D. That is converted based on this function, and then you can take the combination. Okay, x1 with y1, x2 with y2, like that. Does it make sense?
Yes.
Now, if we just print, so I'll share this code. So then probably you can play around it. You'll see that. Now you can see this is the combination, right? It looks like a 2D point, right?
Yes.
X1, Y1, X2, Y2 like this, right? But if you see this here, since actually I use the same variable name, so that's why it's so difficult to again run. So here actually it is separately it is given, right? And oh, sorry, no, yeah. So here it is separately given. So basically you need to combine them, minus 0.5 and 0.5 as a 1 point, right? And that is his here.
Yes, sir.
Now it makes sense? Perfect?
Yes.
Okay, so now basically this SI grid is basically the 2D data points which contains the mesh grid x coordinates in the first column, and second column contains the second coordinates, or the value of the intercept. Okay, now once I have this data set, I can do, I can calculate the error, right? Okay. Is it fine?
Yes. Yes.
Okay, so for this different combination of S and I, actually I'm just calculating this deviation, the absolute deviation, and as well as the square deviation. Okay, and then I'll talk about this part, but just thing. Okay, so now you can see this red dot is basically the ground truth, right? Where actually the actual solution is present, for which actually the solution is optimal solution, right? But if you vary from, if you just change your data points from, let's say, from that point to some other range, from 0.5 to 3.5, then throughout the space you are expecting this kind of representation of error. And what exactly it implies, that like if you see the bar, that near the point in between, let's say 0.5 or 0.0 to 3, the error is not that high. But whereas if you took some combination in the corner, right, this corner, let's say in between minus 0.5 and 0.5, right, or 1.5, this range, then basically you're expecting more error, right? So this visualization will help you to understand that how far you actually move to a space to get back a good solution, to get a bad solution. So that means that which part of the parameter space will give you a bad solution, and which part will give you a more or less a good solution. Okay, so, so this is just a simple representation for the absolute deviation. Similarly, you can also get back for the square deviation, right? For square deviation, you're getting sort of representation. You can see if it is a center in a 2D, and you're actually the less error actually varying in a ellipse shape, right? So that means basically along this direction or along this direction, you have a very small error. But once you have actually like finished with your ellipse representation, and if you move some other point in that space, then basically your error will be very high. Does it make sense?
Yes.
Right. So what is implies? It is implies basically, for at least for the square definition, implies that if you make a distribution for the error, let's say it is an ellipse, right, and you have a center, that is the actual solution, and if you deviate from your that center, then you're actually you're getting some normal distribution, and that normal distribution is basically showing what kind of error you're getting. Okay, so I don't know, like, does it make sense or not? But normally, like in statistics, it's very important to understand like how this error is actually deviating over the space.
Right.
Right. So, but like no one asked me that here actually, can someone tell me that what exactly I'm doing here? I'm just varying my slope and intercept value, right, in between some ranges, right? But how I know that what is the actual value I'm getting? Because if you see, when actually I'm calling this function absolute deviation and this square deviation, we need to check this function, right? What I'm doing here, then when I'm calculating absolute deviation, basically what are the parameters I'm sending? So this params contains two. It is an array of two elements which contains slope and the intercept, and I'm also sending that x, y, and y error, right? So I know what is the actual y or the actual value, and what is the error term which we added, right? So basically, it's calculate for each point. It calculates the original y and the predicted y, and then it is normalized that by the error. Okay, and that's why we know that how that error can be propagated throughout the space. Does it make sense? Because I was not sure that either it is clear to all of you that how actually we are getting the actual y value, because we are calling here directly this, we wrote this lean function, this line model, right, a linear model, and obviously from like once you have those m1 m2 or m and c value, it's actually calculate what should the y predicted, right? Does it make sense? So let's say if you're sending m equals to 1.5 and c equals to 2.5, right? Then obviously your y prediction is very good, right? Which we already showed in the previous example here, right? If you choose actual whatever the m and c which is nearby the actual one, right, then your fitting is very good, and your error should be very less, right? Any comments, anything it's not clear or something?
Understood, sir.
Understood, right? Okay. So the point is, for different combination of m and c, you need to again predict what's the value of y, and then you need to subtract out from the original one, right? Otherwise, in this space, you will not see any kind of this kind of representation. You will see it completely like uniform, right? But that is not the case. So that means if for every combination of m and c, you're going to actually check what should be the y prediction based on your linear model, or you can directly call your linear regression function, right? So okay, so now I can again change. So here actually I think I am using the second case, right? But yeah, so I was using the option 2. Now option 2, it is very clear that this square error, actually has some specific distribution, right? And it is coming from a Gaussian. Fine.
Yes, sir.
Now, can you tell me what kind of distribution it has?
This is not
Sorry. I'm not able to hear you. Can you please?
Sir, it is Gaussian.
Yeah, it is also Gaussian, but since it's zoom version, right? Because here actually if you think about ellipse, actually is described by two principal axes, right? So your actually the principal axis is very long, and therefore the ellipse the error ellipse is very high, very longer ellipse, right? And therefore in this range you are not able to cover the whole ellipse. Whereas when you are taking for the square deviation, is actually cover the whole ellipse in that range in between 0.5 to 2.5, and therefore you can get the full ellipse thing. So that implies that when you are talking about the error propagation is always a ellipse, at least for 2D or higher dimension. That is normal like a description or like definition when you're considering some noise, right? But the width and height of the ellipse can be varied based on your different combination of M and C. Fine. So it may not look like, okay, it is coming from same Gaussian distribution, but it is actually the same. But here the sigma is very high as compared to the previous one. This from this one, right? Fine. Yeah, I'm just trying to give those visualization which might be already like read theoretically, but you have not seen anything like that practically. I don't know how many already seen this kind of error propagation or the error distribution over the current space, but this is the way normally we try to look into or try to build up some statistical model. Okay, so that is for this option 2, right? Now I can just see, I can just show you that what should be the distribution for the option 1. So so I'll just quickly run that so that like we can directly see the value. See, now what you got here? So you get a ellipse, but the second principal axis is very like it has one directional. Basically, it's like the second principal axis is very small, right? So it's like a very thin ellipse, right? And for the second case, it is not only a thin ellipse, but it also has the like very like very small perturbation. Like the ellipse is very small, right? So based on different noise realization, this error propagation can be different in the space. Okay, does it make sense?
Yes.
Okay, so next this visualization, I hope it's fine. Now I'm going to like already I showed this. Okay, you can solve this linear regression problem using mathematical or linear algebra, right? You're solving a matrix equation, inverse matrix problem, considering inverse matrix problem, right? That we already did yesterday. Now same thing, if I want to estimate what should be my MNC from a statistical point of view, how I can do that. Okay, so that is the important part, because as I said that normally in the data there is noise is present, right? Or that means there are fluctuations there, and that fluctuation can be like described in terms of some statistical distribution, and we showed that okay, that has some specific structure in the space, right? In that M1 M2 parameter space. Okay, now I just want to show you that okay, if I want to estimate this value of M and C in from the perspectives of like statistical thing, though it is similar to the your this mathematical relation, but in statistics how are you going to describe this thing? So right now I already described this is the error, right? This x this chi-n equal to yn minus yn prediction divided by sigma. Similarly for the chi-n square is similar, right? So then for chi-n square this can be written in terms of y minus x theta square by sigma n square, right? So this is written because we're assuming that this yn predicted value actually coming from a algebra solution, considering x is a coefficient matrix and theta contains all your variables, right? So yesterday I showed that okay, that x can be a two-dimensional, like it is n cross 2, so it has a two column and it has n number of data points, right? And theta can be c and m, and this y is the y, all the y data points, right? So I can replace this yn predicted from our algebraic relation in terms of x and theta. Fine.
Yes.
Now if you see this representation, I can just write this square in terms of metric representation by considering y minus x theta and y minus x theta transpose. Fine. And now if you want to write, if you want to plug in this sigma n square in between that, then you can actually write another matrix, that is capital sigma inverse, and where the sigma contains all the small sigma in diagonal, right? So if you take the inverse of this matrix, become basically 1 by sigma 1 square, 1 by sigma 2 square, like that, right? And that can be basically your sigma inverse.
Yes, sir.
Fine. Now you can think about, this is basically the error propagation, right, through the space, which I already showed earlier, numerically, right? Just consider different data points or different combination of M and C, right? So ideally, whatever way you consider different combination of M and C, it should actually provide a distribution in terms of this representation. And this is basically a Gaussian distribution. Maybe I don't know how many of already aware of that, but if you write your like normally you already aware of like one-dimensional Gaussian distribution, right? But if you go for a higher dimension or multivariate Gaussian distribution, there might be some scalar part, like constant part 1 by 2 sigma, something like that. But ideally, this actually looks like a Gaussian distribution, because in higher dimensional space you need to also consider this sigma part also. That sigma part actually implies that what is the relation between your the variables, okay, that the parameters for which you are going to solve this equation. So so right now, as I mentioned, that sigma is basically sigma contains all the sigma square, but this is just a very specific example, and that's why we're assuming that all the variable doesn't have any specific correlation, right? So this is basically a covariance matrix. Actually, it's a variance matrix because it has only the variance element in diagonal, and the off diagonal doesn't have any like non-zero element, right? But if on the off diagonal element also are non-zero, then it is basically a covariance matrix. So this whole error propagation can be represented in terms of statistics by considering a covariance matrix, right, or variance matrix for this case. Does it make sense?
Yes. Yes.
Okay.
Similar analysis are used in time series analysis also, no?
Yeah.
Yes.
Okay. So this concept is very important, that the variance and the covariance of a data, because whenever you're going to talk about real scenario, you can't get a direct solution in terms of a good fitting. You need to estimate the error. So this is important. Now what I can do, we know that this if you want to talk about the error, this is the error. Now what we need a best optimal solution of the theta in that space, right, to get back the actual solution good, right? Because y prediction is depending on what kind of theta you're getting, right? So if you're getting a very good theta, then obviously that will provide the best solution, right? So our goal is to identify what should be the best theta, right?
Yes, sir.
So now if you solve this equation, so it's now like it's an optimization problem, right? That okay, if you choose different theta, you'll get different error propagation, but you need to find out for which theta this is actually providing a very small error propagation, right? So that is a sort of called as a numerical optimization problem. And and I don't know, like let's say if I ask you that, okay, try to find some, like I give you a function and I ask that, okay, can you tell me that where this function is optimized, or like can get a maxima or minima? So for that, what you normally do that you calculate the differential equation, right? You solve the first order differential equation, second order, like, so if you solve this, if you solve the first order differential equation in terms of theta, then basically you get the solution, this theta opt, in this way. So I have not shown the mathematics part. You can go and do this algebra, that if you do a derivative from this, actually I intentionally I skip that part, because directly we are not going to integrate this this theta. Basically we need to first define a likelihood, that is basically the Bayesian analysis, which I'll talk about tomorrow. And that likelihood actually considered this part. So ideally, for this problem, for linear fitting problem, first you need to define a likelihood, that we'll talk later tomorrow. Maybe I'll try to keep the connection with this example, but let's say that we have some likelihood, and that likelihood actually contains this expression. And therefore, when you're going to minimize that likelihood expression with respect to theta, then basically you'll get this your solution. Okay, so right now just consider this is a solution. But if you want, you can go and do the exercise. Or I mean, I think in very standard statistics books, all the books has this solution. So you can go and check. So so basically, if you solve a differential equation considering this expression, then basically you'll come up with the actual optimal theta in terms of this representation. Okay, and this is really crucial. Obviously, this part is as if I remember correctly, yesterday I also showed that if you talk about pseudo inverse, right? Pseudo inverse also similar representation, right? There sigma was not there because in pseudo inverse we are talking about in terms of matrix representation, but here actually it is similar because you are actually considering it is higher dimensional space. That's why you are adding the sigma. So if you are talking about like in a one dimensional space, sigma is basically 1 0 1 0 1. It's identity matrix. But if you're talking about in high dimensional space, it should be a some non-zero component also. So that's why it is similar. And this specific representation has a specific structure. So we'll try to see what kind of structure it has. Does it make sense?
Yes, sir. Okay.
So yesterday I showed that, okay, first we need to generate this matrix, right? So I showed that, okay, we can generate individually this column and this column separately, and then you can like join them together to get back this X, right? But that is a trivial way, or like that is a simple way of doing that. But there's a specific like matrix representation in NumPy that's called vendor. If you call that function, then basically you can directly get that representation. So you can see, so this basically X contains all the first column 1 and the second column is basically all the data points, X data point. Fine.
Yes.
Now what we can do, we can actually see how to compute this thing. So first of all, we are defining this sig. Sig basically is this capital sigma, right? And this capital sigma is nothing but like I just make a n dimension, like just maybe I can do it this way. So if you print this sig, right, this sig contains like all the diagonal elements contains basically. So your yes. So the y error and others are 0. So no need to. I hope it is fine. So if you write the NumPy diagonal element, then it is basically making a diagonal element with this sigma square. Okay, so this sig is equivalent to this one, and what we need sigma inverse, right? So we need to take a sigma inverse also. So we can generate the sigma inverse, right? Now I can show two cases: noise-free case and the noisy case. I don't know what happened to noise case. Okay, yeah. So what I mean by noise case and noise free case, because like as I said, the solution is in terms of this, right? And here actually you can pass your y, and we can use the previous y, right, at which there is no noise there, and it's just all the points in a straight line, right? And we can also use a y new, which actually is basically some like deviation from the actual thing. And for both the cases, you can see what kind of representation you're getting for this C, right? So okay, so we actually, I just write the expression here in terms of this whole thing, right? But considering the actual y, okay, that's why it's called noise-free case. And then I can get the C considering C is basically this expression, and then you can get this covariance matrix. Fine. Okay. Now, like it is very simple way of writing that. Okay, I just multiplying. What I did, I just multiply first. Let's say for C, I did multiply in between X transpose sigma inverse here, right? X transpose sigma inverse here, and then actually I multiply again with the X, right? And then I'm taking the inverse, right? But if you want to use like a direct linear algebra operator, then you no need to write in this way in terms of the dot product. What you can do directly, you can write what are the matrix you want to multiply in terms of this at the rate. So if you write at X transpose at the rate sig inverse at the X, that actually do the multiplication in terms of this. Okay, so you can check that both are actually giving a same or not value or not. So if you print this C and C1, then you can see both are exactly the same thing, right? So that means basically you can either use this expression or either you can use this expression, whatever you want, right? So now I have that covariance matrix. What I can do, I can calculate the eigenvalue and eigenvector. Can you please tell me someone like why I need to calculate the eigenvalue and eigenvector?
So they will be the diagonal elements, right? Directly.
Yeah, and then that is right now because we are assuming that it has there is off diagonals are directly 0, right?
Yes.
But in some cases, if it is not 0, then you need to calculate the eigenvalue, right? I am completely agree with that right now. This sigma x square and sigma y square, right? They are actually the eigenvalues. Basically, it is just 1 by lambda. So they are actually inversely scaled with this lambda for this case, right? But ideally, the covariance matrix should have also then the off diagonal terms, right? And for that, we need to calculate the eigenvalues and eigenvector. But the point, what I'm asking that why we need to calculate the eigenvalue and eigenvector? Anyone? No? So I said that we need to see geometrically how this covariance matrix looks like, right? We need to see what kind of representation we have regarding this covariance matrix, right?
Yes.
So now you can see the dimension of this covariance matrix is basically 2 cross 2, right? And if you just print it, this is this covariance matrix, right?
Yes.
Now this covariance matrix, if you calculate the eigenvalues and eigenvectors, what eigenvalue and eigenvectors implies in that space, that you can okay, since it is 2 cross 2 matrix, it should have 2 eigenvalues, right, and 2 eigenvectors.
Yes.
It might be possible they are same, they might be different, but ideally it should have 2 eigenvector and 2 eigenvalue, right? So eigenvector actually provide you the direction of your error in terms of this C matrix. Right. So think about that. Okay, I have two vectors, the first eigenvector and second eigenvector, right? So they can have some angle, right?
Yes.
So they have some angle. So that actually help you to understand what kind of rotation or what kind of like when in which direction your eigenvectors are, right? And eigenvalue actually help you to understand what should be the amplitude or what should be the scale of for that those eigenvalues or eigenvectors, right? So yeah, practically, when you're talking about in terms of this statistics, when you're talking about in terms of eigenvalue, eigenvector, basically you try to understand how the data actually visualized or how data actually are placed over that space in which direction and what is the scaling factor for that. So scaling factors can be calculated based on the eigenvalue because eigenvector actually are ax equal to lambda x, right? So basically you are solving that x. AV equal to lambda v is the eigenvector, and the lambda is basically the eigenvalue. So your v actually is scaled by your lambda, right? So from origin point, the eigenvalue can provide you the scale of your eigenvector, and eigenvector can provide you the rotation or the representation in which direction it has all the points, right? So that's why we need to understand what is the direction and what is the scaling factor. Does it make sense?
Yes.
Okay. Now, once I know that what are the eigenvectors, so I can calculate I know that okay, the eigenvector has some angle, right? So I can calculate the angle also. So here actually we calculate the angle. Okay. And we actually consider that basically eigenvalue. So the width and the height of that ellipse can be actually varied based on the square root of this eigenvalue. So that we calculate as W and width and height. So now we'll try to see. Okay, so now you can see that this is the direction of your ellipse in that space, right? So this is basically your ground truth, and this is the direction of your ellipse, right? And now what I did, I just choose 3 different cases, like 1 sigma, 2 sigma, 3 sigma. So I'm not sure like how like if you aware of these terms, 1 sigma, 2 sigma, 3 sigma or not, but aware of, right? So in basically in statistics, you need to measure that how far you are from your actual solution, and that is basically based on the deviation, right? And the deviation terms basically sigma. So if you're saying, okay, I am away from 1 sigma, in between 1 sigma, that means like where it is little bit less. If you're saying, okay, I'm in a 2 sigma, then basically a little higher. If you're saying, okay, 3 sigma, that's a little longer. So in this direction, you can say the 3 sigma basically the longer ellipse, right? And 1 sigma is basically a small one. So it's not clearly show like visible here, but maybe I can change it a little bit again. Sorry. So I need to rerun again. So maybe I can just fix this option 1. I can see what is sorry. So I need to run the first from the beginning. So I think better to. So any question you can ask, like I need to rerun this thing. So to show for different for the second case how it's actually propagates. But any questions till like if no, is question clear to everyone?
Yes.
Yeah. So it's either it implies the very simple thing I am talking about, or you are like I don't know, like maybe all of you already aware of this kind of thing, right? So how many already have done this kind of analysis earlier?
So like we had our this subject in our coursework as an elective.
Okay, but have you like visualized those error the way actually I was showing today?
We have just seen the plots in the books. That's why.
Oh, okay. Like you are familiar those plots in terms of. So like now it can verify that okay, you can also make a similar kind of plot, right?
Yes.
Yeah. Thank you. So these are the very like I hope it will be useful for those who are going to use in the upcoming days regarding this kind of analysis. So maybe when I was reading all those things that time I was struggling to understand these things unless actually I was doing myself. So hopefully now you can see for this case it is very clearly understood, right? So 1 sigma is basically small ellipse. 2 sigma is another ellipse which is little bit longer as compared to the first one, and third ellipse is this one, right? And that means the width of your distribution. So if you make the Gaussian distribution, that width of the sigma can be varied, right, for 3 different ellipses. So direction is fixed, right? Direction for all the ellipses is fixed, but width can be varied based on your what kind of error you're getting. Does it make sense?
Yes. Sir, can we say that scaling is based on that eigenvalue?
Yeah.
The scaling of these ellipses is based on that eigenvalue which we calculated.
True, but no. So like that is true, right? But right now what I did here, you calculate the eigenvalues, right? First, yes. Right, and then you calculate the width and height. That is basically square root of your eigen lambda, like 2 into lambda, square root of lambda, right? Now for 3 different cases, it is not like you're comparing directly with first and second together. Right. So for the first case, this is the scaling of your eigenvector. Yes. So let's say this is one direction here, right? So this is scaled by whatever the eigenvalue it has. Yes. Similarly, for the second case, it actually from the truth. What should be the eigenvalue, right? Now, from that, if you check what is the optimal value you're getting, then you set the optimal value is 2.5, 1.5, right? Why I'm very much sure that this is the answer, because you can see I just plotted the truth value. And truth value actually lying exactly there, and all the first, second, third sigma actually surrounding that as a center point, right? So if your theta optimal is not exactly the original solution, then what you expect, that you are expecting the solution should be in the same direction. Direction is actually in this direction, right? But it might not be aligned with the center. Yes, sir. Okay, so that maybe I can show you that, because this is a noiseless case, right? So for noiseless case, obviously we are getting the solution with exactly same solution. Therefore, we are expecting that okay, that our original solution should be in the center, and your sigma can be propagate in this ellipse with consider that as a center point. But for noisy case, let's say I do the noisy case, right? Now noisy case, you can see ground truth is here, right? So your actual this error propagation actually deviated from your ground. So that's why the ground truth is actually not in the center point, right?
Yes.
Does it make sense? So in this case, actually, I have not plotted the predicted one because the predicted one, the grounded one, the truth one is ground truth are exactly same, right? So that cyan dot and the red dot exactly overlapped here. But in this case, it is not overlap, right? That means actually you are getting similar kind of error propagation in terms of this Gaussian distribution, but the direction of the original ellipse is not same as this one. So the direction of the ellipse can be little deviated, right?
Yes.
Does it make sense? Okay, so now if you just check the what is the top you're getting, so you're getting the top equal to 2.44 and 1.53 for this example, right? So I just try to compare here. So you can see this is the ground truth 2.5, 1.5. This is the value you got from your linear regression fitting, and this is the value you're getting considering your covariance matrix structure and the statistics, statistical representation, right? So for the same problem, you're getting two different solution or two different answer, right? Considering two different approach, and you can say this theta opt is the using this statistical or covariance structure, data structure, covariance structure. It's giving a better approximation as compared to this one, right?
Yes.
Right. So that means linear representation, linear fitting may not be the correct way of looking into that, rather than looking to try to understand what are the correlation between the data points or the variables and try to estimate the covariance matrix in this way. So any question regarding this exercise? And you need to if you any doubt, please tell me, because tomorrow I am going to extend this exercise to some further analysis. So that actually helped me to understand. If you have some doubt, better to tell me right now. Anything? No?
And sir, like, have you shared like these notebooks?
I'll share by today. So sorry, I was not able to share the yesterday notebook, but by today I'll share both the yesterday's and as well as today's notebook. Okay. Any other questions? So I need to check the chat box. No.
No.
Okay. So I think I have for 12 more minutes, right? So I can talk about one more topic, which is basically another regression, which is very useful. But this is not mathematically similar the way you're talking about linear regression. This is called logistic regression. But this topic is very, very useful in terms of some advanced analysis. So so right now I'll try to give the notion. Let's say like obviously, as I said, that the regression or the fitting is actually depending on what kind of data structure you have, right? So if you visualize data, if the data is actually is not if it is in a straight line, then you can at least you can understand there are linear relation between those variables, then basically you can fit a linear fitting. But if it is not, then you need to understand what kind of relation it has, right? So logistic regression is one kind of regression which actually helps you to understand that basically it actually partition between it's supposed to divide the data points into two parts, and you can say okay, it can be one coming from one specific class and another is coming from another class. So I can show you what exactly I mean by that. So let's say I just generate some random data set. So I hope this will very, very clear. If you, I'll share the code. If you're not able to understand, just please let me know tomorrow. So I just generate some data points, random data points, right? So I just generate 100 data points randomly, and let's say I just try to with 10 data points first. So I just generate some 10 data points X, and what I'm doing, I'm just considering okay, Y is my another variable which basically is giving some kind of ground binary relation, that okay, if X greater than 0, then it will be a true or true, and if it is less than 0, then it's a false. That means what it implies that okay, for this data set, this point is greater than 0, right? For that means we should get Y equal to true. Similarly, for this data, it is a minus, so that means it is less than 0. So for that, we should get false, right? Because this is the way I made my binary table, right? So now, if I convert this Y data set into a numerical representation, then it should be like true is equivalent to 1, and false is equivalent to 0, right? So it is equivalent in hypothesis. Like in the statistic, when you're talking hypothesis, null hypothesis is always a true, like give a true information distribution. That was always a true representation. That is one, and alternative hypothesis maybe always give a false representation. That is 0, right? So in this way, you can write your y in terms of one binary representation 1 0. Does it make sense? Fine, right?
Yes.
Okay. So now actually for this data, let's say this is my data right now, right? So you can see this is my data points in x-axis and this is my y, right? So y is nothing but only 0 or only 1, right? Now for this data, are you able to fit with straight line? No, right? The answer is no. So for this kind of thing is sort of like you need to think about some kind of classification problem, considering that okay, whenever you're getting 0, that means they are actually nearby points, so they are part of one specific cluster, and these points are actually part of one specific cluster, right? So you can say okay, here there is a two specific class 1 and class 2. So whenever you're getting 1, that means it's a part of class 1, and whenever you're getting 0, that means a part of class 2.
Right? For such cases, we can use the Fermi-Dirac distribution, right? There also we have 1, then it drops and 0.
Yes, exactly same thing, right? So right now I'll just talk about how we're going to solve this in terms of the logistic regression. Okay.
So it will be something like 1/1 plus exponential.
Yes, exactly. So that is the logistic regression, like the characteristic profile of the logistic equation based on that. But right now, since I'm talking in terms only the 0 and 1, so I'm just writing that that the logistic equation can be written as a like a ratio between two different two different hypotheses. That is, one is null hypothesis and one is alternative hypothesis. So that's actually defined as the ratio, that's the odd ratio in Bayesian analysis. So we are going to stick to that part, but the way you are defining that is also true. Fine. Yeah. Okay, so now if you define the log odds, basically it's basically what saying it is a p is basically providing a the probability of your actual class, and 1 minus p basically is the providing the probability of the false another class, right? So it is like when you're doing the probability, right? You define what is the probability of getting some specific hypothesis and what is probability of getting some alternate hypothesis. That's why you're dividing this log ratio in terms of p by 1 by p, and whenever you're getting 1, then basically it is p, and whenever you're getting 0, this basically the probability 1 minus p. So basically this logistic regression has to solve the problem considering probability. So it's actually giving some probability value. Okay, so now I'm not going to talk about how mathematically you can do that, but like right now we have a specific function in the sklearn, this logistic regression, with that directly we can call, and then we can fit, right? So that we did, and we can find out what is the like coefficient intercept, and that is required because the way you want to say that, like it should be 1 by 1 plus e to the power that specific value of am mx plus c. For that it is required, and now what are the score you can get from that? Data, it is important. So okay, sorry, what happened? Oh, I have not maybe oh, so I missed the confusion matrix. Just a minute. So I need to check confusion matrix there from where. So this should be from we are here, right? So we can plug in this one, and then it should run.
Sir, like you need to read it.
Oh, it's sorry, what happened? I'm not able to hear you. Can yeah, so now you can see that like after fitting what the value you're getting, some prediction value, right? Some probability. So it's like it is a part of class 1 or class 2. It's like a part of null hypothesis or alternative hypothesis, right? So now you can see if you compare this to value, this value is high, right? So this value is that means it's a part of your second class. So it's a part of class 2. Similarly, here actually the value is here high, right? So it's a part again part of class 2. So until this also part class 2, this is class 2, this is class 2, but here actually it's a part of class 1, right? So based on this probability, you can decide either it is a part of class 1 or class 2, right? So now this is also, it is a part of class 2, this is a part of class 1, this is part of class 2, this is part of class 2, right? Now if you just see the y prediction, then you can see that, okay, this is for the 0, this is for the 1. So this is 1, then 1, then 1, 1, 1, then it is 0, right? Then again 1, then it is 0, then it is 1, then 1, right? Does it make sense?
Yes.
Now, out of this, you can see for all the data points, it's actually giving 0. That means basically the prediction is correct. Only there is a 1 point at which it is giving -1. That means for that it is a prediction is wrong, right? So it might be possible that for some cases the prediction is wrong, but for that you can see that the score is 0.9 because out of 10 it's actually giving correct answer for 9 classes. For one class it is not giving correct answer. That's why it's 90% accurate, right? And if I make this confusion matrix, basically you can see out of this 10 data points, right? 9 data points actually correctly classified, 1 is not correctly classified. And if you want to make this as like a visually appealing, so you can say that, okay, actually it is 0. Like 2 times it was 0, it's actually giving a 0. 7 times actually it was 1, and it's actually giving us 7, right? And only 1 time it's actually it was 0, but it's actually giving 1, right? This is the wrong answer. So whatever the value you're getting the offline off diagonal, that should be the wrong thing, right? Now now I can just use let's say 100 points, right? So I can generate some 100 points. I can make the same class, then in terms of binaries, and then the data points, and then same thing, right? So you can't directly see this prediction, but what you can understand that almost it is giving a correct answer because it is a score of for 99% accurate, right? And then you can see the confusion matrix basically for 19 out of this 100 data points, for 99 data points, it's actually giving the correct class. For one data points, it is not giving a correct class, right? And if you see the confusion matrix, there also it is very, very clear. Does it make sense?
Yes.
So rather than talking in terms of fitting numerically, what you are considering for this this problem, that you are considering, okay, if data point lying here, then basically it is part of one class that is defined by 0 or 1, and for this it is 0, right? So it is basically dividing the whole space in terms of 2 different classes, right? And you just want to predict that, okay, if actually it is a part of class 0, then it should directly lie here, right? Because it should give the value 1 always, right? So that's the way you can actually talk about this fitting. Now just I think I already crossed the time, right? Sorry. So can I just get 2 more minutes? Oh, I have 2 more minutes, sorry. Yeah, okay. So now that is, I need to just it's not to call here, so it is just okay. Now for the same data, what I do, we can fit in a linear model, right? And we can predict also, right? And for the same thing, we can find out what is the loss for the logistic thing, and now we're comparing what is the value of result we're getting from linear and logistic, right? So now you can see these are the data points, grade 1, and this is the logistic regression basically shown by this S curve, right? This is S curve, I think it's called S curve, and your linear fitting is basically this, right? So the linear fitting is very, very bad as compared to logistic regression. So that means for this kind of data, where you actually, there are very, very pretty much clear that, okay, one set of data actually part of one specific class, and the part of one set of data is part of another class, and another is a part of another class, then basically you need to use logistic regression rather than considering a straight line fitting. And that's a really important concept when you're going to talk about the classification. So if you're going, let's say if you're going to classify between 2 different images, let's say a dog image or cat image, right? And you need to identify for a given new image which either it is a should be go to the dog image category, or it is should go for a like cat image category, right? So that prediction can be done using logistic regression, but it cannot be done based on linear regression. right? So this kind of nonlinear representation or nonlinear relations may not be directly possible to solve in a linear regression thing, but logistic regression can solve this. Does it make sense? Okay, so I think I just finished. I just this all, yes, it's 12, so I can stop here and I can continue again tomorrow.